if you could remember, in the last lecture, we were studying a correlator binary or two types of signals or binary signaling. We saw that correlator is a type of a detector. So we saw this channel, and then we it's type for demodulators. We have a demodulator and we have a detector. So first we will be studying about demodulators, and there are two types of demodulators. First one was a correlation type demodulator, and we then studied the correlation type demodulator for binary antipodal signaling, and it was shown that the output of this detector will be a Gaussian random variable having SM mean and n0 by 2 variance. So this will be the probability of y given Sm, where m could be 1 or 2. This could be y given S1, y could be given S2, and the probabilities you can see they are given here. For y given S1, this will be again a Gaussian random variable mean shifted to under root EB, while for y given S2, this will be mean shifted to minus under root EB. Now, this was clear, but there were some steps which I just explained by words in my lecture. So the mathematics was not given. So, but I found that actually these steps were also given in Dr. Tahir notes, which we are also doing side by side with our lecture representation. So if you see these lecture 20 notes, you can find some of the mathematical steps which I just explained by words. They are actually written in detail, so you can very well see them. So if you can remember, when we were studying this correlator, so we said, all right, this will be a signal, it will be this will be received signal, it will be multiplied with the basis function, and this will be sigma square, this comes out to be 1, and this was noise with the orthogonal function 0 to TP. This will give you some number which will be n, and there I said that n will be a random variable, a Gaussian random variable, and here you can see that because n was actually a white noise process, so its sample will give you a Gaussian random variable, and then the Gaussian random variable will be multiplied by an orthogonal function. So there is a rule in, you can say, probability union algebra, that if you multiply a function by an orthogonal function, then its distribution doesn't changes. So you have a sum of Gaussian random variables. You will sum them up, you will again get a Gaussian random variable. All right, that is why n is a Gaussian random variable. So you need to find the mean and variance of this Gaussian random variable. Mean will be definitely 0, as you can see that this is the function. If you find its mean, or you find mean of E on both the sides, expectation on both the sides. On the right hand side, this is a deterministic function. This is random, now a random variable after sampling. So this, it is a white process whose Gaussian mean is 0. So that is why the mean of n will also be 0. In order to find the
variance,
sir. Yes, Gigi.
सर ये जो अभी आपने बताया कि जो n of t तो रैंडम वेरिएबल हो गया, जो हम एंटी रैंडम प्रोसेस है इसको किसी टाइम पे सैंपल करेंगे तो n of t आपके पास रैंडम वेरिएबल आ जाएगा,
लेकिन गॉसियन रैंडम वेरिएबल आएगा क्योंकि आपके पास वाइट नॉइज प्रोसेस था
जी। अब जो psi of t है ये तो सिंपल डिटरमिनिस्टिक फंक्शन है ना, तो हमें कैसे पता है कि ये इस रैंडम वेरिएबल ऑर्थोगोनल है? और वैसे भी एक तो रैंडम वेरिएबल एक फंक्शन है, तो इनमें ऑर्थोगोनैलिटी का क्या सीन है?
ऑर्थोगोनैलिटी का क्या सीन है? अच्छा, ऑर्थोगोनैलिटी का क्या सीन नहीं, देखिए ना, एंटी को छोड़ दें, ये तो एक रैंडम वेरिएबल हो गया, ठीक है ना। तो वैसे इन जनरल रूल क्या है कि जब आप दो रैंडम वेरिएबल्स को मल्टीप्लाई करेंगे तो तो उनकी जो स्टैटिस्टिक्स है दैट विल चेंज।
सर लेकिन एक तो इसमें रैंडम वेरिएबल
सॉरी,
नहीं ना, ये
हाँ नहीं
साइड
चलो
ऑफ
ठीक है,
वो तो
हाँ आप सही कह रहे हैं। चलिए अगर आप किसी कांस्टेंट नंबर से भी मल्टीप्लाई फर्स्ट करें, वैसे तो एक फंक्शन से मल्टीप्लाई करें, अगर आप किसी कांस्टेंट नंबर से मल्टीप्लाई करेंगे तो इसकी ना कहीं तो स्टैट्स में चेंज आएगा ना, उसकी मीन या वेरिएंस पे।
सर ये मेरे ख्याल ये जो इंटीग्रल है ये बेसिकली क्या एक लीनियर कॉम्बिनेशन नहीं है इनफाइनाइट नंबर ऑफ जीरो मीन रैंडम वेरिएबल्स का?
बिल्कुल बिल्कुल,
यही है।
मगर असल बात ये कि जब आपने इसको मल्टीप्लाई भी किया ना साई टी के साथ, साई टी एक ऑर्थोनॉर्मल फंक्शन है, ये आपने याद रखना है ना। मल्टीप्लाई करने से इसकी स्टैटिस्टिक्स में कोई फर्क नहीं पड़ेगा, ये गॉसियन ही रहेगा मल्टीप्लिकेशन के बाद। और जब आप उसको एडिशन भी करेंगे तमाम गॉसियन रैंडम वेरिएबल्स को, फिर भी आपके पास एक रैंडम वेरिएबल गॉसियन ही आएगा। ये तो वैसे ही रूल था रैंडम गॉसियन रैंडम वेरिएबल। जी
लीनियर कॉम्बिनेशन उनका दोबारा
वो तो
गॉसियन
ठीक
ही
है, हाँ
रहेगा।
बिल्कुल सही। इवन
तो
मल्टीप्लिकेशन
सर
भी आप करते हैं ना ऑर्थोनॉर्मल के साथ, तो उसकी स्टैटिस्टिक्स चेंज नहीं होती, वो गॉसियन ही रहता है।
लेकिन सर जब इस इंटीग्रल को हम एक्सपेंड करेंगे तो ये जो n t है ये किसी कांस्टेंट के साथ मल्टीप्लाई होगा ना, फिर तो ये मतलब ये फंक्शन तो नहीं रहेगा। जब इस इंटीग्रल की टाउ की डिफरेंट वैल्यूज पे साई ऑफ t की कोई वैल्यू होगी और वो उस रैंडम वेरिएबल के साथ मल्टीप्लाई हो रही होगी, तो ये एंड में लीनियर कॉम्बिनेशन ही हो जाएगा इसका।
हाँ जी बिल्कुल, वो बिल्कुल सही है, लीनियर कॉम्बिनेशन ऑफ गॉसियन रैंडम वेरिएबल्स ही होगा। मल्टीप्लाई करके भी रैंडम वेरिएबल ही रहेगा गॉसियन, और ऐड करने के बाद भी एक गॉसियन रैंडम वेरिएबल ही रहेगा। इसकी जो एक्चुअली पीछे बहुत बड़ी थ्योरी है, वो एक्चुअली हमारे कोर्स में नहीं है। अगर आप इंटरेस्टेड हो तो ये एक है, हमारी बुक है फंडामेंटल्स ऑफ वायरलेस कम्युनिकेशन, बाय डेविड शे के नाम से है। अगर आप इंटरेस्टेड हो तो सॉफ्ट कॉपी मेरे पास अवेलेबल है। उस पर एक्चुअली इसको डिस्कस किया हुआ है कि गॉसियन रैंडम वेरिएबल्स जो हैं वो एक रैंडम प्रोसेस के बाद जब आप उनको डिस्क्रीट भी बनाते हैं ऑर्थोनॉर्मल फंक्शन से मल्टीप्लाई करने के बाद, तो वो क्यों एक रैंडम वेरिएबल ही रहते हैं। तो मतलब ये एक वेल डिफाइंड थ्योरी है, और मैंने इसको कोशिश की है शॉर्ट बयान करूँ। एक्चुअली बुक में तो कुछ दिया हुआ नहीं, तो मैंने बस आपको ये बताया कि जी वो सेम ही रहता है। अगर आप इंटरेस्टेड हो तो आप जो है रेफरेंसेस पे देख सकते हैं, जो एक में से मैंने नाम लिया, वरना वैसे इसके अलावा आप किसी भी प्रोबेबिलिटी की प्रॉपर बुक हो जिसमें लीनियर अलजेब्रा प्रोबेबिलिटी, तो उसमें भी चीज़ें मेंशन होती हैं। ठीक है, तो यही वैसे छोटी मोटी आप टोटका याद रखें कि ऑर्थोनॉर्मल फंक्शन से स्टैटिस्टिक्स चेंज नहीं होते। ठीक है, भला डिटेल्स चाहिए तो आप क्लास के बाद या फिर वैसे ना, ये कोर्स का हिस्सा नहीं है, ज़रा मुश्किल कॉन्सेप्ट है, मास्टर्स लेवल का कॉन्सेप्ट है, तो इसको हम ऑफ टाइम में ज़रूर जिक्र मतलब डिस्कस कर सकते हैं। चलो मैं कोशिश करूँगा इस वेडनेसडे से मैं अवेलेबल भी रहूँ 1 से 4 अपने रिसर्च टाइमिंग्स में। आपको पता है पीसी का विजिट है, उसकी वजह से थोड़ी सी प्रॉब्लम्स भी हो रही, काफ़ी ज़्यादा काम बढ़ गया टीचर्स पे, बट इंशाल्लाह मैं अवेलेबल हूँगा इंशाल्लाह। तो आप ज़रूर आएँ, क्वेश्चंस पूछें, और हम कोशिश करूँगा आपके कॉन्सेप्ट्स हैं वो क्लैरिफाई हो जाए। अच्छा, लेट अस गो फर्दर। मैं क्या कह रहा था, बस मैंने सिर्फ शो करना था कि ये भी एक गॉसियन रैंडम वेरिएबल ही रहता है। ठीक है, थोड़ा सा मैंने आपको आगे ले गया। अगर आप नहीं जाना ना जाएं, बस आप ये याद रखें कि ये रैंडम वेरिएबल रहेगा, एक गॉसियन रैंडम वेरिएबल ही निकलता है। सो इफ इट इज अ गॉसियन रैंडम वेरिएबल देन you can find its mean and variance. So its mean is 0. Now how can you find its variance? ठीक है, so variance of a zero mean random variable is just e of n square, because mean is 0, तो eta square तो इसका 0 हो गया, that is why it is just e of n square. So what is e of n square? It is n is this thing, it is integral, so 2 times the integral, double the integral. N square means double this integral, so that is why this is double integral. This was also given in the book, but what was not given in the book, that I wanted to emphasize. Now we know that NT is a white noise process, and its PDF or its spectral density is given as follows. This was also discussed by me in the last lecture, but I couldn't show this mathematics, so I should have shown that. That is why I am showing it here. So we know that the Fourier of the autocorrelation of a white noise process is like this, and its Fourier inverse or its autocorrelation is just a del function. So I will just replace. You can very well see that this is the autocorrelation function of the white noise process. Just r of tau likhte hain, t minus tau. This is the time difference between these two. This will be this thing. So this thing is is a del function which is tau, which is now here is t minus tau. वहाँ तो हम tau पढ़ते हैं ना, t into t nt और t plus tau, the difference tau था, यहाँ पे तो t और tau है, it will be t minus tau. All right, so you can just write as del t minus tau. All right, now once you place this as del t minus tau, so you know what will happen. This del t minus tau will force t to be equal to tau, because you know this del function only exists at the point of impulse, or you can say the point when its argument is 0. So its argument will be 0 when t will be equal to tau. So this means that this t will become tau. So this t becomes tau, this becomes like this, and rest of the things remain the same. So this tau is tau squared, this goes out. Inside the integral with dt you will have this integral, n naught by 2 is constant, but we all know that area under the impulse, you know, even from infinity to infinity is always 1. So, you know, even from 0 to t it should be 1, it comes out to be 1. N over 2 comes out, and we all know this is an orthonormal function. It's, you know, its energy has been normalized to 1 and all that has been studied. This comes out to be n naught by 2. So its variance comes out to be n naught by 2. Hari Salman sahab, are you understanding?
जी सर, ये समझ आ गया था लास्ट टाइम.
Acha. So now we know that the output is signal plus noise, where this noise is a Gaussian random variable with mean of 0 and variance of n naught by 2. This means that y will also be a Gaussian random variable, because this is a Gaussian random variable, and you are adding you are adding s of m. You know s of m was what it was just a number, but it was just a scalar number by which you were scaling your you know orthonormal basis function. So it was just one number. All right, so a number, a discrete number plus a Gaussian random variable means that you will still get a Gaussian random variable. And what will be the mean of y? Mean of y will be mean of this. Deterministic value will come out, mean of n is 0. This comes out to be s of m. I ask you, Haji, what is the variance of y? What is the variance of y? Okay. So what will be your answer? You say, all right, e of variance of y will be equal to e of y square, because y is also a zero mean random variable. You can also prove it from the basic formula. So what is e of y square? All right. Oh, sorry. E of no, I'm sorry. Because you know e of y will be s of m, because e of y will be e of sm into e of n. E of n is 0, so e of y is s of m. Okay, but what will be variance of y? All right, now please see a little bit difference, which I actually forgot. Remember that variance of y will be equal to e of y minus its mean. Now y minus it means y minus sm, because mean of y is sm. Sm cancels. This means that variance of y is equal to variance of n. Variance of y is equal to variance of n. हाँ जी, समझ आ गया सबको? How come variance of y is equal to variance of n? Can you prove this? अरे सलमान साहब, समझ आ रहा है ना?
जी सर, ये तो वैसे लीनियर कॉम्बिनेशन था, तो इसमें तो वैसे ही होता है कि वेरियस ऑफ y इज इक्वल टू a स्क्वायर इनटू वेरियस ऑफ x होता है. तो a इसमें 1 था, तो ये वैसे ही वेरियस ऑफ n के इक्वल आ जाना था.
सही. चलिए सर, मगर इसमें शायद कंफ्यूजन होती है स्टूडेंट्स को कि भाई ये एसएम भी तो आ रहा है ना. मैं याद रखें जब आपने वेरियंस
लेकिन सर वो
निकाली
कांस्टेंट है,
माइनस
वो
का
तो
वेरियंस.
वेरियंस में नहीं आएगा.
हाँ
a स्क्वायर वेरियंस ऑफ x आ जाएगा सिंपल.
जी. नहीं, अब याद रखें वेरियंस का फॉर्मूला क्या होता है? रैंडम वेरिएबल माइनस द मीन स्क्वायर एक्सपेक्टेशन.
सर वो
So you
लीनियर
have
कॉम्बिनेशन में जनरलाइज हो जाता है ना. ये लीनियर y उसका वो था ना, लीनियर कॉम्बिनेशन था. तो लीनियर कॉम्बिनेशन के केस में आप सिंपल डायरेक्टिव भी निकाल सकते हैं. तो y इज इक्वल टू
हाँ, आप
अगर
सही कह
ax
रहे हैं.
plus b हो,
वेरियंस
तो वो a स्क्वायर वेरियंस ऑफ x हो जाता है.
वो भी आप ठीक कह रहे हैं, बिल्कुल सही कह रहे हैं. चूँकि वेरियंस में एडिशन से फ़र्क नहीं पड़ेगा, सही कह रहे हैं. मगर उसके अलावा भी मैं चाहता हूँ स्टूडेंट्स थोड़ा सा ये भी क्लियर हो जाए कि जब आपने y का वेरियंस निकालना है तो उसका फॉर्मूला क्या होता है? y माइनस द मीन. तो जब y में आप मीन माइनस करेंगे एस एम कट जाएगा. सिर्फ n ही बच जाएगा ना आपके पास, ठीक है।
जी सर, जी सर,
ये भी
सही
समझ आ रहा
है।
है ना आपको, ये जो पॉइंट है मेरा,
यस सर।
ये सारा देखें यहाँ पे ये चीज आ गई। तो output of correlator is a random variable with mean of Sm and n naught by 2 variance is a Gaussian random variable. So you can write this as a PDF as a density function. Y given Sm will be mean of Sm. So you know y is shifted to Sm. Variance is n naught by 2. So 2 sigma square, 2 to cancel, this becomes n naught. You know this was also 2 pi sigma square, 2 to cancel, this becomes pi n naught. And Sm could be, it could be anything. It could be under root EB, it could be minus under root EB, depending on what type of modulation scheme you have used and how it has been mapped onto any of the orthonormal bases. S1 and S2 are these two things. Hence, you get these density functions. Y1 given S1 for under root EB, and you can draw the other density function y given f of y given S2 for minus under root EB. So it will lie here, and this Gaussian distribution will lie over under root EB. Next, we study the same correlation type demodulator, but this time we use the binary orthogonal signals. So we know binary orthogonal signals, again they can be given in terms of the basis function, and normally we choose the basis functions in such a way so that you know why these cross product S1 2 and S2 1, they are 0, and phi1 is defined from one function, phi2 is defined from the other S2 function, and both of them we have seen that S1 and S2 are actually both orthogonal. This could be your S1, this could be your S2, and you know this will be S11 side 1T, this will be S2 side 2, and then you have a AWGN channel, so noise will be added, and this will be the received signal. So the received signal, your correlator will look like this. Now, as far as previously, you can see that for the antipodal you just have psi because you had only one orthonormal basis. But for orthogonal signaling, you have two orthonormal bases, so you will need two correlators, one with psi 1, one with psi 2, again the same integral, and then you sample it at TB, and the output will give you y1 and y2. Previously you were just getting y, and now you will be getting y1 and y2. You can see that y1 will be with psi m or psi 1, y2 will be with psi 2. 0 to TB, so that you will be sampling at TB. Now, if I assume that S1 was transmitted, then from the first correlator, what you will get? First correlator will be y1 into psi 1. So if S1 was transmitted, so S1 plus n tau into psi 1 tau. So you can see there all are tau. It's just multiplication and then integration. So S1 of tau we just saw it is actually S11. And all that. If you will multiply, you will get psi 1 square, and this will be n with psi 1 t. So you know psi 1 square is 1, this will become S11 plus n1. Again, you can check that n1 is actually multiplication of n with the orthonormal function, and then the integral. This comes out to be n1. So this will again be a Gaussian random variable with definitely zero mean, but with variance of sigma square by 2, which you can verify yourself. Similarly, the output of the second correlator will be assuming that S1 was sent, this was a signal for S1 plus noise into psi 2. So we psi 1, psi 2, and you know psi 1, psi 2, they are both they are always orthogonal, okay, orthonormal, which are orthogonal, so this will be 0 and you will just have n2. So output at the second correlator will be n2. Total output will be now a vector under root EV plus n1 for y1 and n2 for y2. EV plus n1 for y1 and then n2 for y2. Similarly, if you say that S2 was transmitted, then again you will get Y1 and Y2, but for Y1 you would just get the noise because S2 will be with psi 2 and Y1 is with psi 1. Psi 1 with psi 2, that will be, orthonormal, that will be 0, you only get noise. But for Y2, you have psi 2 and S2 is also psi 2. Psi 2 becomes psi 2 square and you will get the energy of S2, which is under root EP. So we already see that n1 and n2, they are Gaussian and a variable with 0 mean and not by 2 variance, and the output is a vector that depends on n1 and n2. We need a joint statistical characterization of n1 and n2 to characterize the output vector y1 and y2. This looks that it becomes complex because now you have a vector on which you have to decide, but it can be simplified assuming that n1 and 2 are independent. So once two random variables are independent, then you can very well see that the joint distribution is equal to the product of their individual distribution, provided they are independent. Very famous rule. So fn1 and 2 will be equal to fn1 times fn2. Now, how can we show that n1 and n2 are independent? So what we do, we find the uh, cross correlation of n1 and n2. Alright, so you can see it will be again the same formula. This will again give me delta because uh, alright, so you have n1 and n tau, and again this is white noise. Autocorrelation will be delta t minus tau, and again we have seen that this will make delta 1 tau, and again you will have delta 1, but this time delta 2. So this is again orthogonal. This will give you 0. So the cross correlation is 0, but you can see I can also write en1 n2 as en1 times en2, because en1 is 0 and also en2 is 0. Alright, so I can write en12 as en1 into en2. This means that they are uncorrelated, as their cross correlation is 0. So they are uncorrelated, and we know for Gaussian random variables that if we have uncorrelated random variables, then this means that those random variables are also independent. Hadi Salman sahib, have you read this in your previous course that if Gaussian random variables are uncorrelated, then this means that they are also independent?
सर ये आपने पढ़ाया था पीछे चैप्टर 5 में.
मैंने पढ़ा दिया था ना. हाँ, मुझे यही था सर. चलिए ठीक है, यू कैन. ऑलराइट,
सर
थैंक यू,
इसमें
थैंक यू. हाँ,
ये आप क्रॉस कोरिलेशन कह रहे थे, ये क्रॉस कोरिलेशन है या ऑटो कोरिलेशन है? क्योंकि रैंडम प्रोसेसेस में नहीं है तो ये ऑटो नहीं होगी.
हाँ, आपके वैसे ऑटो एक्चुअली होता है कि वैसे ना एक ही रैंडम प्रोसेस से अगर आप लें उसको,
तो सर ये एक के दो सैंपल्स हैं. n1 n2 एक ही प्रोसेस को दो जगह पे सैंपल करके दो रैंडम वेरिएबल्स लिए हुए हैं.
थोड़ा सा फर्क है ना। अगर तो एक ही जगह से होता फिर तो मैं शायद मुझे ऑटो ही कहना चाहिए, तो फिर तो मैंने गलत कहा। मगर आप देखें n1 n2 आ कहाँ से रहा है, n2 कहाँ से आ रहा है?
सर वो n ऑफ t को सैंपल किया हुआ मेरे ख्याल में।
नहीं बिल्कुल
तो
ठीक है, मगर देखिए ना प्रोसेस देखें, प्रोसेस n2 का प्रोसेस देखें कहाँ से आ रहा है। यहाँ से आ रहा है ना, कैन यू सी द
जी
कर्सर?
सर।
अच्छा
जी
n1 का
सर।
प्रोसेस क्या होगा? वो यहाँ से आ रहा है। ऑलराइट, सो दैट इज व्हाई वी आर सेइंग दैट, आप ये कह सकते हैं कि बेस में उनका बिल्कुल सही कह रहे हैं, नॉइस प्रोसेस था, मगर फिर जिस फंक्शन से आपने गुजारा है वो थोड़ा सा डिफरेंट है दोनों के लिए। ठीक है, तो आप उनको बेहतर है कि उनको दो डिफरेंट रैंडम वेरिएबल्स कह दें। इसी जब दो डिफरेंट रैंडम वेरिएबल्स हो गए तो फिर मैंने उनको क्रॉस का वर्ड कह दिया। मगर आपने ऑटो कहना है कि जी, आप कहना चाहते हैं कि जी उनका स्टोकेस्टिक प्रोसेस सेम था, तो चलें आप कह लें, इतना कोई फ़र्क नहीं पड़ता। मगर वैसे तो ये क्रॉस को रिलेशन ही बनता है, क्योंकि कोवेरियंस में तो क्रॉस डालते हैं फिर वो ज़ीरो आता है, तो फिर वो हम कहते हैं कि वो अनकोरिलेटेड है, अगर दो रैंडम वेरिएबल्स आपस में ज़ीरो हो जाए। आप कुछ कहना चाहते हैं, ऐड कर लें कि नहीं तो फिर हम पिछली बुक में भी जा सकते हैं, वहाँ एग्जैक्ट डेफिनेशन देख लेते हैं।
नहीं सर क्लियर है, मैं तो बस वैसे टर्मिनोलॉजी को पूछ रहा था, क्वेश्चन।
हाँ बेहतर ही है, मतलब कि आप कहना तो कह लें, मगर ऑटो कहना थोड़ा सा ना मुझे लगता है ठीक नहीं है, क्योंकि अब n1 n2 दो डिफरेंट जगहों से आ रहे हैं ना। मतलब ठीक है बेसिक सेम था, मगर उसके बाद तो आपने दो डिफरेंट एक फंक्शन लगाया ना, जिसने डिफरेंट तरह से उनको मल्टीप्लाई किया और सब और मतलब इंटीग्रेट किया, दो डिफरेंट फंक्शन से मल्टीप्लाई किया। इसीलिए मैंने फिर आप दिखाना चाहते हैं कि जी कोरिलेशन जो है वो ज़ाहिर है आप उसी रैंडम वेरिएबल के साथ करेंगे, फिर तो बात ही ख़त्म हो गई ना। तो कोरिलेशन आ रही है, तो आप अनकोरिलेटेड दिखा रहे हैं दो डिफरेंट रैंडम वेरिएबल्स को। तो बल मैं इसका वर्ड चेक कर लूँगा, शायद मैं टर्मिनोलॉजी गलत ना यूज़ कर रहा हूँ, मेरे ख्याल से वैसे ठीक है, मगर आई विल मेक श्योर दैट इट इज़ राइट। ऑलराइट, so now we know that they are independent. So once they are independent, you can write the joint distribution as product of their individual distributions. So I can write this as f of y given s1, and this will be f of y2 given s1. So you know f of y1 given s1 was just noise, and f of y 1 given s1 was noise plus the signal. Mean was shifted like this. So both these PDFs have been driven. So I've just put the values of y1 given s1 and y2 given s1 from previously determined distribution. ये देखिए हमने पहले determine किया. So we have चलिए वो इधर इन्होंने बनाया हुआ नहीं, but you can very well see that y1 was this random variable, ठीक है, and we saw its इन्होंने यहाँ पे इसकी PDF लिखी नहीं नोट्स में, मगर चलिए हम लोग लिख लेते हैं। but you can see that y1 will be a Gaussian random variable with mean of delta EB, and variance will be n naught by 2. All right. So when y1 given s1, because this was calculated when s1 was sent, so I just wrote that distribution here, which is mean shifted to under root EB and variance is n naught. For y2 you can see that mean was 0 and the variance was again n naught by 2, hence it comes out to be 2 n naught by 2 into 2 into n naught by 2, 2 cancels, comes to y2 square, and these terms will be same for both of them. That is why this will be 1 over under root pi naught for this term, and again 1 over under root pi naught for this term, so they both multiply, and that is why there is a square. So if I say given s2, then y1 will be noise, and y2 will have its mean shifted, and so this will be the PDF of y1 y2 given s2. So in general you can all right, so this is taking it further, so let us try to understand. Now this is the same thing which I have told you, that y1 given y1 y2 given sm is actually, you can separate this because of their independence. So y1 given sm multiplied by PDF of y2 given sm. So if I say that the sent signal was S1, so this will become Y1 given S1, Y2, Y2 will be just noise, and Y1, will be shifted to under root EB, root EB, this is Y1, and Y2 is just noise, it is around 0 with variance of N naught by 2. Aji, I think everyone is understanding how you are getting these figures. हाँ जी सलमान साहब, समझ आ रहा है ना आपको ये फिगर्स कैसे आई?
जी सर.
All right, so we have ended this notes, we move to the next notes. So I know I can go to the book also, but I have found that the notes are more explanatory in nature, so that is why I'm sticking to the notes here, but we'll be going to the book at the appropriate junction or junction. All right. So the last notes, they concerned a correlator for orthogonal or antipodal signal. Now let us go to another type of demodulator, and that is called the match filter type demodulator. And you can see in the book also, book में भी उसने दोनों का जिक्र किया. देखिए ना, पहले है correlation type demodulator, this we have discussed, and then these examples which we have not discussed. You can do it by yourself. If I get time, I will discuss them also. And this we have studied now. Then he discusses the second type of demodulator, which is called the match filter type or match filter demodulator. So again, for this type of demodulator, we will discuss its performance for antipodal and so we discussed the match filter for antipodal signals, where you had one basis function. So in a match filter, you have a signal, it goes to LTI filter, and you get the output which is sample n. That will be the output of the detector. Now here, what should be my impulse response of the linear filter? So the impulse of the linear filter has to be a matched response. And this filter response is given as psi TB minus T. So it is matched to the orthonormal basis function, which was actually psi of T. This is psi TB minus T. So what will be the filter output? Filter output will be the input signal, which is R of T, and I convolve this with H of T. This becomes R of tau, H of T minus tau, D of tau. Now what is H of T minus tau? So we know that H of T was TB minus T. All right. So H of T minus tau, whenever you put a T, it becomes minus T. So if I put T minus tau, this will become TB minus T plus tau. All right. इसलिए सब्स्टिट्यूशन की इसकी कोई ज़रूरत नहीं है, जिससे मैंने आपको समझाया दैट इज़ मोर देन इनफ. सो ये ऐसा कर देंगे. मैंने अपने नोट्स में चले जाते हैं ज़्यादा सही से समझाया मैंने. So yes, we know h of t is psi tb minus t, but what will be h of t minus tau? So whatever the function here, it becomes minus. So this total will become minus. It will be tb minus t plus tau, and then when you sample at t is equal to tb, so this t becomes tb. You know, this tb cancels. We have r of tau into phi of tau. And again, the output will be r of tau into psi of tau. So the same thing is represented here, but Dr. Tai has done two number of steps. The process is the same. You can do any type of calculation. So I follow my calculation. The result will be y of tb will be equal to 45 minutes. So y of t will be equal to r of tau into psi of tau. Alright. So I put the value of r of tau. This is the value of r of tau. You can see here. And now I just multiply. This becomes psi square. This becomes nt into psi tau. Again, you know, this will be a Gaussian random variable with all that properties, mean 0, variance sigma n0 by 2. This is 1. This becomes sm. Hence your ytb comes out to be sm plus n. So the output of this filter is exactly the same as the output that was obtained for the cross correlators. The output that was obtained for cross correlator in terms of binary in terms of antipodal signaling is the same, is equal to the same output when the input signaling is the input signaling is again binary. While the previously, you know, you had a cross correlator, you were multiplying and you were integrating. This time you have a linear filter, but the output remains the same. So what is a match filter? In general, a filter with impulse response S TB minus T. We just saw there. We just saw it was psi of TB minus T. So if your signal is not in terms of psi, it is in terms of S. This will be S TB minus T. Same thing what has happened to psi of t will happen to s of t if the signal is an arbitrary signal in terms of s of t. And a filter whose impulse response is given as tb minus t, or which is the same signal, but you know, actually it is flipped around the t-axis with minus t, and then so this will happen for any arbitrary signal. If you have any arbitrary s of t, then the match filter response will always be tb minus t. You can just see that you are actually flipping it, and then you are delaying it by tb. As an example, you can see this is s of t, so you first flip it, it comes here, and then you advance it by tb, so it will come here. Okay. So again, you know, h of t is stb minus t. So what will be ht minus tau? If t becomes minus t, so t minus tau will totally become minus. It will become minus t plus tau, and you know, tb was sample it. So you can see very well the ht minus tau will be tb minus t plus tau. And again, when t becomes tb cancels, it becomes s of t into s of t becomes s of t square. And this thing, which is the energy of the signal, so hence you get ytb as the maximum value of signal. So again, this shows you that alright. So let us apply the match filter for the binary orthogonal signals. So again, for binary orthogonal, we have seen this will be there. We have this type, and we have already seen this will be 1 1 or 1. You can say it only matches to one orthonormal function. The other one also matches to the other orthonormal function. So now you will have two match filters. One will be with respect to psi1, another will be with respect to psi2, and same values dv minus t with respect to time. We will have two samplers. We have two samplers, and you can see their figures. So output will be as follows. And when you sample at TB, this basically TB cancels, and it comes out to be so you can see that y will be equal to just the multiplication, and we've already seen that this comes out to be psi m tau. Psi tau, and it could, because this is hm, which could be 1 or 2, this could be psi 1 or 2. Values again, you will see this will become sm, psi m square, and this becomes nm. So here again we have used the facts, because you can see very well that the cross correlation terms are 0. That is why it will come like this. Now after studying demodulator both from the perspective of a correlator as well as from the perspective of match filter, we now go to a detector. So there was also one diagram that actually I could not discuss, and maybe I should have discussed it. Alright. We are going into the last lecture. We just finished. It's one point that's not discussed here. So we were designing a detector or a demodulator. First we designed a demodulator, as we discussed recently in this lecture, and but this part was just left. So you can see what happens in communications, that first of all you have an analog signal, you convert it into a DC signal. All right. So now you have into a digital signal. So now you have a bit sequence. Now in order to send this signal, you will again convert this bit sequence in by a modulator into an analog signal. Okay. And once this analog signal comes here, we'll have the demodulator, which we are studying right now, and you will again get a detector that will detect whether 0 was sent, whether 1 was sent, whether none was sent, and that will so you can see analog, this will become digital, and there you will have a decision. Hence you will decide which signal was transmitted. In other words, you can decide which bit was sent. This was just left, I said that why don't left part from the notes also. Now we have the Optimum detector and its performance. This we have discussed. Yes, so we have Optimum detector. Now what is a detector? Now you have a demodulator which actually you can correlate, so which passes through a match filter and then you sample it. So you have a discrete output, which is a Gaussian random variable. Now you have to decide on this discrete output from the demodulator which actual signal was sent. So you can see that you are actually sending, you have actually discrete, but that discrete was made analog, and let's say you have 4 signals that you can send in analog. So that will be respectively psi 1, psi 2, if you have S1, S2 with respect to orthogonal signaling, then you will decide on S1, S2 based on their psi 1, psi 2s. And if you have, for example, antipodal signaling, then you just have psi 1 as the one basis function. So whatever you have this random variable, you will put this into a detector, and the detector will tell you that which signal was sent, whether S1 was sent, whether S2 was sent, or whether the signal corresponding to psi 1 was sent, whether the signal corresponding to psi 2 was sent, or whether the signal corresponding to psi with delta EV was sent, or psi with minus delta EV was sent. First of all, we let us say do with binary antipodal signal where you have one basis function. So we have seen y f of y given Sm, and we have seen y of given S2. And you can also see its PDF that we have driven originally. The mean was delta EB. This we have already done. Fi given S1, S2, you know, this will be just like this. So what is the job of the detector? Detector has to maximize the probability of reduction, but at the same time uh, it has to minimize the error. It has to maximize the probability of reduction. And this which will mean that we are actually minimizing the error detection. So we want to maximize the probability that Sm given y was sent. The given y is received, probability that Sm was sent. So it could be S1, probability of S1 given y, it could be probability of S2 given y, and we have to compare which of the probabilities is greater, whether PS1 given y is greater or whether PS2 given y, whichever is greater. So we will choose that symbol because it has more probability with respect to the so we want to maximize this factor by choosing an appropriate SFM. So therefore, given y, we get that SMM that maximizes the probability. Now we know from the Bayes rule that this we have also studied in our earlier lectures that you know Sm given y is equal to y given Sm divided by you know f of y, but you know sort of it will be first step it will be Sm y divided by Fy. What is Sm probability of SMY can be actually written as probability of so from the base rule, SM given Y will be Fy, and then up in the numerator you will have SM times Y. But in the base rule, the SM times Y can also be written as SMY times probability of SM times Y can be written as probability of Y given Y SM, and Y SM can be written as Y given SM into probability of SM. Alright, this you can also see from the book. This is a very famous base rule. And f of y will be actually sum of all f given Sm with probability of Sm. Alright, this is also given in the previous lectures. So now you will have two probabilities, P of S1 given y and P of S2 given y, and you have to use them so that you can maximize the probability of Sm given y. So we will just compare these two probabilities in which and any one of them, if it is greater than the other, then we will choose that symbol. If this one is greater, then we will say that S1 was sent. If this one is greater, then we will say S2 was sent. So this is like this. Greater, S1 was sent, less than, or this is greater than, this means S2 was sent. Now, next thing is what is the error probability, that you have sent S1 but you detect S2. Now you can see here actually that if you have sent S1, then f of y given S1 should be greater. So normally it is greater than f of y given S2, but at some point you can see here that the probability of y given S1 comes out to be less than probability of y given S2. So for these scenarios, you can very well see that the probability of y given S1 will be less than probability of y given S2, and hence you will say that hence you will say that S2 was sent, but actually S1 was sent. So this means there will be a probability of error. There will be some error here. So from the density plot, probability of error given S1, which will be the distribution of Fy given S1 from minus infinity to the point when this distribution is less than Fy given S2. So for this case, you can very well see that in these times from here onwards, PDF of y given S1 is less than y given S2. So summing from minus infinity to, let us say, 0, 0 might be any other number, let us say alpha in general, from infinity to 0 of y given S1 means you will be able to find the probability of error, because in this region it will be saying that S2 was sent rather it being saying that S1 was sent. Similarly, probability of error given S2 will be Fy given S2, and this will be from 0 to infinity. Let us say that general number is alpha, so from alpha to infinity, from some number in between these two distributions and between S1 and S2 up till infinity, that will give you the probability of error given S2. And the probability of error will be, these marginal distributions with the distribution of the condition PS1 given error given S1, PS2 probability of error given S2. So this will give you the total error. So as seen above, error will be equal to PS1 given ES1 and S2 given ES2. Then we know that PES given 1 is infinity to alpha, while PES2 will be given by alpha to infinity, where alpha is the number where the two PDFs intersect. So how can we maximize our probability? We will take its derivative and put the result equal to 0. Take the derivative, put the result equal to 0, and then its derivative. This rule we have studied, and we were studying chapter 7, that if you take the derivative of an integral having limits, so you will get the function at the points of the limits. The function at minus infinity will be 0. You will just get the function at alpha. There you will get the function minus with minus function at alpha, but you will be minus function at alpha. So you'll get function at alpha. PS1 is already there. PS1 is already there. Then PS2 times a function of alpha. This minus because this was in the lower limit. S2. So 0. So you can manipulate this over this over this. You will get this. You can put the densities of alpha given S1. So alpha given S1 means that you have alpha given S1 means that your mean was S under root EB, while your variance was N naught. So you can just put the Gaussian random variable alpha given S1. Then you can also put alpha given S2 as follows. For S2, the mean was minus 100 dB, so this will come out to be like this. And then you can simplify, this will cancel, and this will go above, and the square terms, alpha square, this will be plus alpha square, it's minus alpha, they will cancel. Even this square of under dB we will cancel, but this will be minus 2ab, this will become plus 2ab, and this will also become minus 2ab, this, and it will go above, this will become plus 2ab, 2ab, this will become 4ab, this is 4ab, and you take log natural on both the sides, this will become log natural, this 1, this comes here, power comes here, and then you can write the power other factors there, and you will get the value of alpha. So you will get this. So this is the value of alpha that will maximize your probability of detection, or in other words you can say that will minimize the error probability. You found this error probability, and then you took its derivative, put it to 0, hence you are minimizing the error probability, or you are maximizing the detection probability, or the probability of correction is being maximized and error is being minimized. You can use an alternate method also, as given in the notes here, but in the exam you can use any other method to get to the result, to get to the boundary values. Alpha was a boundary, as you can see here, alpha defined, alpha gave you this value, this was the boundary value, this is alpha, which actually the two PDFs crosses. So another method is that use this thing, probability of S1 given Y, again same, is greater than or equal or less than equal to ps2 given y. You put the values of ps1 y with respect to the base rule, y given s1 to ps1 and all that, y given s2 ps2, this we have seen. Again you can do manipulations here. Then y given s1, y given s2, again you can put these values, and again you will cancel this will cancel, square terms will cancel, and again you will get that 2ab outside, and you can then put your 2ab here along with other terms. So this will give you in general the value of y with respect to some value where if it's greater than this value it will be s1 and less than this value. What is value? This value is alpha, as it arrives at the cross section of the two PDFs, and so you can find your threshold value from the above method or from this method. Both give you the same answer. Now here you can compare your thresholds for different values of PS1, because threshold is this one. If I say that PS1 is greater, in that case you can say greater, this is small, so overall will be in points, and log will become negative, hence your alpha will be negative, so your midpoint will come here. The reason is that because this distribution is being multiplied PS1, which is a larger number, this will be having greater height as compared to this Gaussian curve. Similarly, you can find for PS2 given greater than S1, that case you can see that alpha will be greater than 0, it will be a positive number. And once they are both equal, then you can see alpha will be 0, as was the first case that we discussed. So if they are both equal, log natural of 1 is 0, hence your y comes out, or alpha comes out to be 1. This we have done. So we have found these optimum values of alpha. Now for this third case, question is what is the probability of error? So we have seen probability of error is actually minus infinity to alpha and alpha to 0, but if alpha is 0, this will come out to be like this. And PS1, PS, let us say they are half. We have assumed they are half because alpha is 0, they have to be half, they have to be equal. So for finding the probability of error, I will first of all integrate this term from minus infinity to 0, and you can see that this term will also be from 0 to infinity, y given as 2, but you can very well see that both these two distributions are same. So half of PS1, half of PS2 will become, because the integrals are the same, you go from 0 to infinity, this will have the same area of the curve as going from 0 to infinity, or going from infinity to 0. You take the negative half, here you take the positive half. And secondly, you can also see that py given s1 is similar to py given s2, because when once y is with respect to s1, so the whole PDF will be at s1 here, the whole PDF will be s2, and but their variance will be the same, so their integral will also be the same. I can write this from infinity to 0, or is also right, and half of becomes 1. Now I can put the value of the function here, this function here. So probability for will be y given s1. For s1 it was this PDF, and you just have to integrate this. We'll be using the q function that I explained to you in chapter 7. For that, you have to normalize this. So what we do is say y minus under root eb is equal to this thing, is equal to x. Hence, y minus under root eb whole square will be equal to x square times n naught by 2. So x squared times n naught by 2 means n naught and n cancel. This becomes x squared by 2. And will come out to be x squared by 2. D of x, you can just see d of x is equal to dy times the constant 2 over under root n by 2. This will come with respect to dx. So you just substitute the value of dx was you substitute the value of dy with dx. So this becomes dx dy, and this under root n by 2 will go in the numerator. This will become 2 over under root n2. So dy will be equal to dx into 1 over 2 under root 2, and then it will become n naught over 2 under root. This will become n naught over 2. This will be your probability of error, and then you can these will be the limits here. You can also check. So if y tends to infinity, definitely x will tend to infinity. So that is there. And if y is 0, then you can see that x will be equal to minus under eb over n naught over 2. This becomes 2 eb over n naught. Consistent. So n naught cancels, this 2 cancels. Sorry, this 2 will come here, 2 pi, n naught cancel. This becomes, you can see this becomes a PDF uh, of a normal Gaussian random variable with 0 mean and 1 variance. And this is the limit. You can use a q function. From the area under the curve from minus infinity to negative number is the same as the area under the curve from this positive of this to infinity. You can just write this as q over this number, okay, because you can see here that this x will come here. So from x to infinity, you have the same area in the curve as for this integral. So you can just write as q of x, where x was this thing. So from here, plus of here going to infinity, this comes out to be this 2 EB over n naught 2. So in this way, error probability has been driven. What will be for binary orthogonal signals? So, for binary orthogonal signals, we already seen that you have this type of form, and this means you have multiplied with psi1, here you multiply with psi2, assuming that psi1 was sent, or s1 was sent, or scalar multiplier of psi1 was sent. So we have already seen that the output of the orthogonal signal will be a vector, a two-dimensional vector. So we need to define thresholding in two-dimensional space. If we first define a generic method, then we'll define a special mechanism later. So from this on, we can do in the next lecture. If any of you has any question, he can ask me. All right. So we have basically we have covered from the book. We have covered from the notes, but you can also cover it from the book. Some of the steps were missing, that is why I have done it like this. There are also certain examples you can see. For example, for the pulse shown in figure 8.6, when S1 and S2 are transmitted, then what will be the so we have a rectangular pulse S1 figure 8.6. So when S1 and S2 are transmitted, this means this is a type of antipodal signaling, and S1 and S2 you can see the n root EB and root minus root EB. The y of t will be SM times psi t. This will finally become psi square t, as we have already done that. So you'll be getting your SMs. So I will take a break here. We'll end the lecture. If you have still any questions, you can ask, because I had to do a lot of work for the power engineering console. That is why I couldn't sleep properly, and then I have having these blots of sleep. If you have any question, you can ask before I end this lecture. All right, so I will end the lecture. Thank you.